So this is all of the stuff in the clouds, so to speak. And now let's return back to the ground. So how are we going to do this course? So we have already talked about the course motivation, why we should look at finite elements. Finite elements is all very flexible and so on. So now let's talk about actually doing finite elements. We'll be dealing with very simple problems here. The diffusion kind of problem, which you can think of a Laplace formulation or Laplace problem. We'll solve it first in 1D polar and spherical coordinates. Then we'll move to 2D and 3D, where we'll actually be dealing with unstructured grids. For that, first we have to understand how the 2D and 3D elements look and how they are constructed. So we'll construct them from scratch. And this will really help you, because just think of it. I mean, you want to combine SPH along with this, right? So how would you do that? You will need this knowledge. So this might seem superfluous if you already have access to COMSOL. I mean, you're just solving in Phoenix. It feels superfluous, but if you really want to unlock the full strength of finite elements, you have to understand all of these polynomials, how they are constructed, and then you have to actually do the meshing along with Gmesh. So we'll do that. I'll show you the structure of the Gmesh export, the file from Gmesh which we export, and I'll give you a script to read that, and then we'll build a solver in MATLAB. I'll also provide downloadable code versions in Python and Julia, and this will give us a lot of confidence to move towards the full-blown Navier-Stokes solvers, which we'll deal in the next course. But at the end, we'll also look at a nice Phoenix workflow, and this is really beautiful because towards the end, when we have written all the codes, we can see that just each block of our code just becomes one line in Phoenix, and the structure and the sequence is so beautiful. And Phoenix is just like a high-end sports car. It works very smoothly, very beautifully. So you'll really enjoy this, the final part. And just to give a more well-rounded end to this course, I have also introduced a GUI workflow, which I have done in FEA tool. So this is the MATLAB toolbox as well as a standalone app. And actually there are so many GUI based tools for finite elements. I have just chosen this tool, and this is just to show you the ease with which you can apply finite elements. But obviously the primary aim of this course is to understand the pseudocode and not just give a GUI tutorial. So let's try to go into more depth and try to understand why we are looking at the Laplace problem. So this is your Laplacian operator, right? Your del square, right? This is your Laplacian, the equation at the end, and you really see this operator in so many differential equations. So I have written down a few of these equations here. So many problems, right? So many physics. Even in case of linear elasticity and Stokes flow, you could reduce the equations in some special cases to terms which have this Laplacian. So there will be other terms as well, but the Laplacian will still be there. So this Laplacian operator is really crucial for understanding any kind of CAE framework, and that is why whether it is finite differences or finite volumes or finite elements, you will always solve a Laplace kind of equations first, and then you will go to the Poisson's equation, and then you will go towards more non-linear problems and so on. So these are some of the test cases that we'll solve. So this is the Laplace equation, del square phi is equal to 0, right? And here we have two circles, right, which are having these direct-lit boundary conditions, phi is equal to 50 and phi is equal to 0, and they are inside infinite domains, okay, or you could even use finite domains. So the idea here is really to use a circle rather than using a square or a rectangle, because we are dealing with finite elements. If we were writing a solver for FDM or FVM, we would rather start off with a square domain because we would deal with structured grids. But in finite elements, we don't have to do that, because in finite elements, the procedure is to map every element to a master element and then do integration on that master element. So this means that you can have elements which are curved, or they are stretched, or they are deformed, and you could map it to a very well-defined, well-shaped master element. And the transformation has a Jacobian, And of course, that is how the mesh is also judged. Jacobian is an important parameter. It tells you how much of it tells you about the quality of the mesh, and we'll have a look at all of those factors as well. But the key point is that you can deal with unstructured grids very easily in finite elements, and the general ecosystem is technically the same whether you're using a box or whether you're using complex shapes. So why not start with complex shapes? And another thing that you can see is the solver which we write for 1D for our polar and spherical coordinates. It will not really change when we go to 2D or 2D higher order elements, or 3D and 3D higher order elements. It's almost the same code. Okay, so it's very easy, and that's partly the reason why finite elements is so good for multi-physics applications. In finite volumes, you cannot really crank up the order from first order element to fifth order element so easily, but in finite elements it is very easy. And in finite elements, another benefit is that the boundary is very tangible. It can be dealt with a very tangible and tractable way. So for example, if this was a heat diffusion problem, if this phi was your temperature, you are solving for heat diffusion. Del square T is equal to 0. That is your heat diffusion equation. And if these two circles were just having these direct light conditions for temperature, you would again get this kind of a solution. And now let's say if you want to calculate the flux at these boundaries, you can just take what is called as a reaction force at these boundaries, and we'll see how to do that. So it's a very simple operation. You just extract the nodes on the RHS and you sum them up. Okay, so it's as easy as that, calculating the flux normal to the surface, because you get these normal flux terms naturally in your weak form. Okay, and this leads us to a lot of benefits. For example, even if you have a boundary which is, so instead of a rigid cylinder, if this was a bubble, okay, if we were talking about liquid-liquid interfaces, you would be integrating a traction or the stress jump along this interface. And even if this interface was deforming, perfectly the normal would be, so the force or the traction would be perfectly normal, and you could calculate those normal components. You could also deal with the tangential component. So it's very easy to deal with the boundary in case of finite elements, and this will actually become easier to understand when we go to the CFD course, which is the next course. But we'll have a look at the reaction forces in this course as well, and you will see how easy it is to calculate the flux at these boundaries. We'll also look at problems which are very simple problems, like this sphere in 3D, which is really placed in an infinite domain. Okay, so we'll use something called as infinite elements to really model the solution towards infinity. Right, and I think in COMSOL you have a toolbox which deals with infinite elements, and this gets really complicated as you start dealing with multipole problems. So for a monopole problem you could really do it easily, but for a multipole problem it gets difficult. So we'll solve the most easiest case, and we'll also solve this kind of a problem in 2D, in 3D as well. We'll do this meshing and in Gmesh and solve it ourselves. We'll also solve it in Phoenix. So now let's start looking at what are the benefits of this, right? I mean, how does this relate to physical phenomena? So thinking of this problem with infinite domain, so you could think of this as a magnet and with a decaying field, but in a reverse way you could also think of a magnetic field which is far field at infinity, and it is interacting with this magnetized with this material which can be magnetized at the center of the geometry. Okay, so let's look at one such case. So think of a submarine which is moving through the sea, and the far field is the Earth's magnetic field, and it is interacting with the submarine. So this interaction causes basically a change in the magnetic flux, and this you will see this as a magnetic signature of this submarine. And you could have a magnetic mine which can detect submarines or ships based on their magnetic signatures, and it can attack them and basically cause an explosion. So to avoid that, we need to stealth the submarine, and we do this by degaussing. That is, we run a wire on the hull of this ship or the submarine, and we apply a flux in exactly the reverse direction, the exact amount of flux in the reverse direction, and cancel that magnetic signature. You could think of a very similar idea in aircraft as well, but there you are not dealing with this del square phi kind of term. You are dealing with an equation for radar waves. So you don't just have a magnetic potential here. So you will have to solve a slightly more complicated problem, but the idea is similar. Let's also look at where these two cylinder kind of problems are used. So you could think of, for example, an arid region in which you have bore wells for extracting water, but then you also have rainwater harvesting and injection wells as well, which will inject this water, harvested water, and increase the water table. Right, and you could also think of a flow of water from this injection point to the extraction point, and this is happening through porous media. The soil is a porous media, so the equations that are applicable are Darcy's equations, and they also contain a del square kind of term. So that is one application which is very different from the previous one. You could also think of two cylinders, heating rods, right? So that is so we have gone from soil mechanics or Darcy flow to directly heat diffusion. You could think of coaxial cables, two circles or one cylinder and a circle placed concentrically. You are solving for the capacitance. And you could also think of electrochemistry or batteries, which is a really hot topic, right? So, of course, the media is really still. There is no convection here. But then the next step, you could also start a convection if you want. The very basic problem is, of course, the diffusion problem. And the way you bring reaction into picture is you have a flux condition at this boundary, which is also coupled to a source or sink term. So that is basically a Robin term, and the kinetics obviously come from thermodynamics, right? So you can look at the scope of applications, right? And mainly all of these applications require complex geometries. All the geometries in real life are complex, and you might require higher order approximations as well. You require tools. You might want to use equations or model equations which cannot be represented directly as flux equations. You might want to deal with moving boundaries or materials which are fracturing and so on. So finite elements is that ecosystem which allows you to model all of this. It does it very accurately, and it also does it very easily. So that's really why we should be interested in finite elements. It's a multi-purpose tool, and it has so many applications just beyond our commercial toolboxes as well. So even as an experimentalist like me, you could gain a lot from it. So this is really what I wanted to talk about in the introduction, and since teaching is my passion, please give me your feedback. So this is a free course like the previous one, and I don't look at this as an opportunity, but I look at it as a passion. So I sleep well because of this. So you can bother me about this. If you have any questions, or if you feel I have left anything incomplete, please tell me and give me your feedback and help me make finite elements more accessible. So I thank you for your attention, and now I'll meet you again in the next talk, where we'll actually start off with some nice coding. So thank you again, and I'll see you.